Konnichiwa, and welcome to my talk with the title, Why AUTOSAR Fails So Often.
So, excuse me? Why AUTOSAR fails so often? Are we not at an AUTOSAR conference? So, what is this? Is this an offense? Is it maybe a revolution? Well, actually no. So with this talk, I would like to point out some of the common AUTOSAR problems and also point to possible solutions. So with the given time today, I'm only going to pick some of the solutions. So there's actually a whole pool of solutions, but yeah, in 20 minutes, there's only time for really just a few approaches. So this is actually an insight from someone who's been out there in the field, coaching, consulting several projects and seeing some of the problems occur again and again and again. And this is why I thought maybe it's a good idea to present those at the AUTOSAR conference. However, before I do that, I would like to talk a little bit about German culture. So, and when I mean German culture, I'm not going to talk about this guy. Does anybody know who that is? Bach. Yes, exactly. Johann Sebastian Bach. So I'm a great fan of him. And we're not going to talk about this guy. Beethoven. Very good. So we turn this conference into a quiz show now. So who's that? That's Friedrich Schiller. And well known for all the German language institutes. You probably heard of Goethe. Okay, so we're not going to talk about these guys. Instead, I would like to talk about the German culture when it comes to working together, and also about, German way of communication sometimes. Okay, so the following slide actually is not to be taken too seriously. It's a certain tendency, okay? So, the question is, where's the opponent? So what I observed around the world happen quite often is this kind of setup, where we have the customer and the supplier, maybe this is OEM, and this is a tier 1, and the customer is superior. So the requirements from the customer must not be questioned. Okay, so he has the power, must also not be criticized. And for some scenarios, this is not effective. And if you work with German engineers, very often you see this kind of understanding and setup where
The customer and the supplier are on one side, and the opponent is the technical problem, or maybe the software is, and then they work together to tackle the problem. Okay? And sometimes the communication between these two can be very honest and very direct, and well, this is very often seen as not very diplomatic. Okay, so that guy here, the supplier, might tell the customer, hey, your configuration is actually rubbish. Not very diplomatic, but maybe necessary sometimes to really tackle the problem. Okay, so don't take this too seriously. With this, I'd like to show you the structure of my talk. We already ran through the warm-up. I'll give a brief introduction of myself before we then get technical and look at common AUTOSAR problem number 1, the RTE overhead. Okay, and then we'll look into common AUTOSAR problem number 2, the non-terminating ECC tasks. And finally, I'll run off with this summary. Okay, so brief introduction of the company. So 21 years in the meantime, we are looking into timing, stack, memory analysis. It's a German company, roughly 60 employees, and we see annual growth around 20%. Focus is strictly automotive around the world. Not very strong in Japan, but I'm very much sure that this will change in the near future. A few words about myself. I founded the company, I'm the CEO. I see myself as a very technical CEO, so I'm actively involved in firefighting coaching projects, these kind of things around the world. I was also quite active in AUTOSAR. I was the RT work batch leader and document owner of the timing analysis work package. Previously with Dieter Bosch, and also author of a book on timing, which is available in German, English, Chinese, Korean, and very recently also in Japanese. Okay, so with this, let's get technical.
What exactly is the problem I'm talking about? So as I mentioned, we do a lot of firefighting at GLIWA, so when the clock is on fire, when there's a timing problem, then we help to solve the problem. And what kind of problems am I talking about? Well, there are things like system overloads, and yet there's functionality to be added. So that's pretty obvious. At that point, you already know you have a timing problem. Sporadic crashes. So the software just stops working. You don't know what's the reason, really. You just see you have a problem. So maybe it's a sporadic problem that only occurs once every few weeks or even months, so difficult to reproduce. Weird functional behavior, communication issues, all kinds of things can have their root cause in the timing, and very often it's not obvious that timing is the underlying problem, and that's why it's so hard to find and solve these problems sometimes. Root cause number one of most of the task forces we've been involved in over the past few years was actually an inefficient AUTOSAR configuration. Okay? The sad thing is that the trend is that this is getting worse. So despite education and us talking a lot, we see more and more projects fail, so the problem becomes bigger. And maybe today helps a little bit to clear up a few things and also point to possible solutions. Right. RTE overhead. Before I can tell you, the background of this problem, we need to talk about what does the RTE do. It does several things, but the aspect I'm concentrating now is ensuring data consistency. Okay, so for example, we have some data structure here, and let's say some task, let's call it task A, starts reading the data from the struct. It gets to the second element, so it has read the second element, and then it gets preempted by task B, so another task with a higher priority, obviously, which then updates the data. Okay, with this, yesterday I learned that this is coral, the color, something between pink and orange. So now the data has been updated, and when now task A resumes execution, it will use an inconsistent set of data. So the first two elements are from the old data set, and the last four elements from the new data set, and that's a problem. Then the software will not work properly. So the RTE avoids this problem by offering data copies. That's a pretty neat solution. So here you can see what actually happens. Again, we have our task A, task B. Here the global data, which gets updated by task B. But now the RTE generates local copies of the data. Okay, so at the beginning of task A, here we've got some RTE code, which will copy the data from the global data to the local copy. Of course, here for the copy process itself, the interrupts need to be suspended to make sure that there's no preemption at this point. And also, if multicore is involved, we need spin locks. Okay, but now task A can really work with the data, and there's no data consistency problem anymore. So, problem solved? Yes. The problem is now that many people don't check what does it cost with respect to RAM, flash, and timing. And this is what I want to make you aware now, that you don't get this for free. And some customers, they really learn it the hard way. For example, this customer here, it's an Asian project, so Asian OEM, and it's actually not just a project, it's a platform. So it's really 19 projects being affected by this. Just look at this big piece of the cake that's taken by the RTE for disabling interrupts, copy, enable, disable, copy, enable, disable, copy, enable. This is a lot of time. This is not what you buy your multi-core processors for, to have them, do that all the time. Certainly not. Second example, and that's a very recent one. The previous one was from last year. By the way, they're happy now, so we optimized the system, all good now. This is a very current project, so I've been there just a few weeks ago. And look at that. Here, MK syscalls, it's a safety environment where you, before you disable the interrupts, you have to run through this syscall. I spare you the details, but look at the CPU load just consumed by this. Let's say that a mechanism required for interrupt suspension. 30% on core 0, roughly 30% on core 1. So 1/3 of the power is again used for copying this stuff around. In other numbers, you can see these values here. I think they're just insane. Up to 340,000 times each second, the interrupts get disabled, copy, enable, disable, copy. This is not what you want, really. Last example, again a platform. Oh, the other one, by the way, was also a platform. Here, 29 vehicles affected. Actually, in the meantime, more projects have been added to the platform, so it's even more than that. The multi-core RX was overloaded already, and yet there was functionality to be added. So they estimated the costs for upgrading the hardware, switch to a more powerful RX to be able to add the planned functionality, and they estimated the costs to be 160 million euros. Can I just underline the number, please? That's 160 million euros. So that's more than 26 billion yen. I don't know how about you guys, but for me, that is a lot of money. So I hope I could make obvious that this is a relevant and very important topic. So, what about the solution? So some thoughts that lead to, as I say, one solution, only one aspect of a solution. So the preemption can cause inconsistent data. Well, if we reverse the logic, no preemption, no problem, right? So one approach is to avoid preemption. The AUTOSAR RTE specification actually states regarding copy semantics, if all accessing entities are in the same preemption area, this might not require a real physical data copy. Aha, so I'm safe even without a copy if they are within the same preemption area. Let me give you one example here for the previous setup. So task A and task B use implicit communication. When assigned the same priority, no copy is required for the data, only these two tasks access. Okay? Obviously, you cannot then access, configure all tasks, use the same priority, obviously. But you can use this as a guidance. Okay? Try to avoid preemption. Only allow preemption where it's really necessary. Okay? If you look at how preemption, the preemption priorities, the OS priorities, the task priorities, how they are configured, sometimes you'll find funny surprises. So possible explanations include the demo project. Our project was based on just had these priorities. Yeah? Or other explanation is like, okay, we have task A, B, C, D, E, which priorities? 1, 2, 3, 4, 5 maybe. Or rate monotonic scheduling, which comes from the scheduling theory, assumes or suggests to increase the priority with the frequency of the task, which from a scheduling theory standpoint makes sense, but it's not always necessary. Yeah? Look at your scheduling, maybe a 10 millisecond task and a 5 millisecond task. Maybe they can share the same priority. Even better than really assigning the same priorities is using internal resources. So then the activation priority is different, but the execution priority is the same, and still no copies should be relevant. And just one hint here to evaluate the potential: do assign all tasks the same priority. Don't try to run the software, it will probably not execute. But you can analyze the generated code and see like how much vanishes, all the copy routines and all these kind of things. And then the sweet spot, the final solution will probably be somewhere in between your current setup and this extreme setup here. And then hopefully your solution looks something like this. Again, another customer example. You can't see anything, but you see that lots of code here just vanished. Okay? And again, a recommendation: look at the generated RTE code to understand what is going on. And this is about awareness. All of a sudden you become aware of the costs of these protection mechanisms. If you just look at the generated code, it doesn't cost you much time or effort, and it's very, very enlightening and helpful. Right. Second example, second pitfall. Guess what? I'm starting again with a customer example. Okay? So, customer called us. We have some sporadic communication problems. Can you help us? So, first question was then, is the system actually overloaded? The answer was no, because if it was, the error hook would trigger a reset. So that was the idea. This is the implementation of their error hook, right? So the error hook being the function, the callback function, called by the operating system at runtime whenever the operating system detects a problem at runtime. And the EOS limit is a failed task activation, which is almost always just an overloaded system. Okay? And what they did now is they placed a system reset in here. And they didn't see any system resets. So their train of thought was, okay, so we don't see any system resets, so the error hook doesn't get called, so our system is not overloaded. Well, the next question then was, are you using the standard RTE configuration? Yes. Ouch. In this case, the error hook doesn't get called. And I'll explain you why, okay? And also then point to a possible implementation, how to avoid this, how to avoid this problem. So, what is defined in the RTE specification? So here, RTE specification, and here some code you can't see, so I kind of magnified it and modified it a bit for the explanation. What do we see? Well, we see some 10 millisecond runnables here, some 5 millisecond runnables here, and everything packed into what is actually a non-terminating ECC task. There's an endless loop here inside the task. And then we've got the event handling here, and then we check which event fired, and then if the 10 millisecond event fired, we call the 10 millisecond runnables. If the 5 millisecond event fired, we call the 5 millisecond runnables. So actually, this here is how you implement a thread in a POSIX system. This is not how OSIG was meant to be. Okay? OSIG tasks are meant to terminate. You activate a task, it starts, and at some point you terminate it. Okay? So what the AUTOSAR RTE actually does is it adds another level of scheduling inside the task. Okay, now we have an operating system that schedules the task, and inside the task we build our own scheduler. So you pay a lot of money for an operating system and then you don't use it. Okay? The whole thing then really gets messy if you start adding regular events, because then you've got these kind of scheduling wait events and then regular wait events, and the whole thing becomes very complex. And yes, it kind of avoids the keep it simple approach. I mean, safe systems, it's always a good idea to keep them simple. The scheduling, the setup. Okay, that's something I very much believe in. So back to the customer example. Let's assume that this runnable here, in some cases, executed for 26 milliseconds. Because this is exactly what happened. Well, a 10 millisecond runnable, a runnable that's meant to be executed every 10 milliseconds, now executes for 26 milliseconds. Well, everyone can see that they have a timing problem, right? So what's the impact now? Well, nothing really, because the AUTOSAR operating system specification doesn't see this as a problem. Events being re-triggered, of course this event here gets re-triggered and re-triggered and re-triggered while the runnable is still executing. But hey, re-triggering events, it's not a problem from the OS point of view. So no error hook, no error indication, nothing. You don't see this. And this is the trace we downloaded. So TT1 was integrated, and we analyzed the problem. We could set up a delta constraint, and then the T1 triggered. We could download this trace. And that was interesting, because now I used PowerPoint, Microsoft PowerPoint, for marking all the locations where the customer would have expected the error hook actually to fire. And this is what the trace now looks like, right? And that was really the moment where the integrator, within 1 minute, he really got pale in the face, had to sit down, because within 1 minute he turned from, we don't have a timing problem, to, we have a massive timing problem. Okay, so what's the solution now for this kind of setup? My recommendation is, well, do not use ECC. Okay, so BCC has many advantages, and again, today we can only pick, some of the topics, or actually only 2 aspects, and this would be my recommended implementation for this kind of setup. You have an operating system, so yes, use it. You want to have 5 millisecond runnables? Well, create a 5 millisecond task. You want to have 10 millisecond runnables? Well, create a 10 millisecond task. Look how easy and straightforward the code looks now. And if something runs for too long now, bam, the error hook will fire, and you will see the reset, and you know you have a problem. Okay? So, straightforward and simple, the BCC1 stuff. Error hook works as expected. This is also the perfect basis for cooperative multitasking. Again, I would love to talk about cooperative multitasking. I'm a great fan. I rarely see it implemented or used, configured. It's a super efficient approach, very, very good, and this is a good basis for it. And maybe just one last side comment. So BCC1, what does the 1 stand for? The 1 means no multiple task activations. BCC2 comes with multiple task activations, meaning that, if this task is still running and you get the next activation, then it gets buffered, and maybe hopefully at some point you kind of catch up with it. Not a good idea. I think the multiple task activations should have never been defined in the standard. I think they're just bad. In 25 years of embedded software in the automotive area, I have not once seen a sensible usage of multiple task activations. My recommendation would be, don't use them. Okay? Stick to BCC1 whenever possible. Right, and that brings us to the summary. So, far too many projects using AUTOSAR are inefficient. Okay, and what we need to really address in the future is that we need to make sure that we don't decouple the, let's say, the specification world from the actual AUTOSAR users. So I would recommend to really check, how is the standard applied in the real projects? How do they use it? What are they struggling with? So to make sure that there's not unlinked here. Okay. Also, more AUTOSAR is not naturally better. Okay, ask this guy. Probably he also at some point thinks that maybe that was a bit too much. And just an idea at this point, we could introduce some safety efficiency subset conformance classes, remove some of the problematic features. So that has been addressed yesterday. So there are paths and thoughts about this already, so that's very good. One aspect I haven't mentioned here, but which came to my mind is maybe we could also come up with, not as part of the specification, but some add-on, some appendix, some, let's say, recommended configurations for, you wouldn't probably need too many, like 4 maybe for different kinds of ECUs, like reference setups as a recommendation. It's kind of following the TT Tech motion-wise approach. So I quite like this idea. Not open up, all the possibilities and all the pitfalls, but, have some recommended setup. And with this, I'd like to say thank you very much for your attention and arigatou gozaimasu.